This is Kunpeng Yao. He's from the School of Computing in the robotics department. He's here to talk to us about advancing robotic dexterous manipulation from grasp synthesis to long horizon task planning. Leave it over to you. We'll have questions at the end if you have them.
Okay, yeah. First, thanks everyone for coming here, and thanks for inviting me today. It's my pleasure to talk about my previous work on robotics, and more specifically to how we improve robotic dexterity in manipulation tasks. Robotics as a becoming a more trending topic is quite hot research field these days, and with the recent advancements in robotics, we see more and more complex and advanced robotic hardwares, especially these humanoid robots, have been manufactured and start to imitate us human performing everyday tasks and also participate in industrial manufacturing tasks. But when we look at these robot skills, we see that it is still quite clumsy and fragile especially when we compare to our manual skills to how we perform manipulation tasks in everyday life. So it is actually quite a hard topic to achieve dexterous robotic manipulation. So there are multiple reasons. So controlling a robot to perform such a task, it's difficult because it requires the control and coordination of multiple degrees of freedom of the robotic system. For example, if you want to grasp an object, you need to coordinate all the joints on each fingers and in your hands, and then you can reach and grasp the object. And second is from the context, because context is how the robotic system, the physical system, interacts with the physical world. There are many factors that affect the context stability, such as the stiffness of the surface, the friction, etc. And also during the task, especially long horizon task or complex task, usually you will see that robotic system may lose vision or lose tracking of the environment, which is crucial to provide feedback to the control system to adjust the robot motions and to plan for the future action. So when we look at, or if we pay attention to how we use our hands to do a variety of tasks, we'll be surprised by how dexterous our own hands are. So as we see, even when we do cooking, yeah. So from our famous British chef Gordon Ramsay. I don't know if you guess he have watched his videos on YouTube, yeah. So actually, this is the level of dexterity that we want our robots to have. So there's always a view that people may think advanced hardware will bring high-level dexterity, which is, I would argue, which is not necessarily true. But if we compare the hardware between our hand and the robotic hand, so by the way, this is one of the most advanced, most dexterous robotic hands on the market right now. So it is called the Shadow Dexter hand, manufactured by the Shadow Robot company. So if we compare the hardware in multiple dimensions, for example, in movement speed, a number of degree freedoms, control frequency, the precision, we will see that. So this is the performance of our human hand, but this is the performance of the robotic hand right now. So we see that robotic hand is actually, it has a much better hardware in many dimensions compared to the human hand. So actually shaping the hand is easy, but shaping the dexterity is a real challenge, and it's what many researchers are tackling in the field these days. So the true dexterity is not only about motor skills, means how the robot system is able to master one skill and perform the skill in 100 times. It's more about generalizability. Because, for example, our hands, we can grasp an apple, but we also want to be able to grasp a different object. I also want to achieve a dynamic interaction. So when grasp an apple, we want to pivot to do some manipulation task on the with the apple, and also we want to use different body lengths. So actually, you grasp an apple with two hands should be not so different from catching a box with two arms. And also, we want to connect all these actions, all these motions to complete a sequential task. So true dexterity is actually the result of both precise motor skills and the ability to generalize them to new scenarios. So in today's talk, I want to discuss three generalizations we tackled in the past. So I will first start with robotic grasping, because grasping is actually the one fundamental skill of the robotic system to enable the robot to interact with the real world, and it is also the prerequisite for any subsequent manipulation tasks. And grasping is has been intensively studied in the field. So starting from grasping, I would like to discuss three generations. So first, generalizations. So first is a generalization to multi-object grasping. So how can we grasp multiple objects instead of one single object? And second is once a robot grasps one single object, how can the robot manipulate the object using fingers, which is called in-hand manipulation. And at the end, so how can the robot perform a sequence of manipulation motions in a long horizon sequential manipulation task? Okay, so first, let's focus on how can we generalize from one single object grasping to multi-object grasping. So currently in robotics field, what we often see is that the robotic hand is tasked to grasp one single object using either the fingertips or the palms to wrap the object, which is called pinch grasp or power grasp. But if we look at how we grasp objects in everyday life, we see that a human hand is so dexterous that the hand explores arbitrary hand surfaces very resourcefully, which is also a very high, which is also a feature of dexterity, is that you are able to use any resource in the system to accomplish the task. And on industrial lines, we see that there are many highly task-specific end effectors or grippers have been manufactured just to grasp or pick up one specific type of object. And also the robot system is usually only able to grasp and to pick up one object at a time. But again, in comparison, so as we humans, our hands are capable of holding multiple objects at once, so which is more efficient. So my question is, how can we enable the robotic hand to achieve human-like dexterity to grasp and hold multiple objects, which is a fundamental problem before manipulating multiple objects in the hand. And before going to explain how we do the work, I want to first introduce one concept which is called virtual finger. So virtual finger, we're all familiar with our finger, which is the real fingers. So virtual finger is a concept proposed by researchers in the 1980s and 90s. So it is the concept. So it describes that there are multiple fingers that they share the same motion and apply similar forces, and they serve for the same functional role in the task, so they can be considered as one finger. So imagine grasping a bottle of Coke, of course. So in this figure, 5 fingers are involved in this task. But all these 4 fingers, they act as a similar role to press against the thumb to hold the bottle. So actually they have the similar motion, they apply similar forces, and they serve for the same functional purpose. So they can be actually considered as one virtual finger. So from this point of view, Let's consider how it simplifies our view on this grasp analysis. Because originally, each of our finger has a 4-degree freedom, one adduction, abduction, and 3 extension flexion degree freedom of our fingers. So if we want to control the hand to perform such a task, we need to control at least a 20-degree freedom at the same time. But with one virtual finger, we can actually use this concept to coordinate all these 4 fingers together. So it largely reduces the number of degree freedom from 16 to 4. So just to mention that real finger, it is a biological concept, and virtual finger, it's a functional concept. When we want to analyze the hand pose, or we want to plan to program any motion of the robotic hand. So key idea is that using this concept, we're able to group multiple degrees freedom into functional units to reduce control complexity. Yeah. So let's see how can we generate one robotic grasp. So this is a hand model. It's a human hand model. It has 20 degrees freedoms. So actually, if we only care about, we think from the point of view of virtual finger, and we only care about where the contact happens in this task. So actually, one virtual finger is associated with one contact. So we only care about that side. We only care about the degree of freedom or the kinematic chain from the base of the finger until the contact point. But we can simply ignore any other degree of freedom beyond this contact point in the robot system. That means we can potentially reduce the number of degree freedoms in the system. And to grasp one object, of course, we need at least 2 virtual fingers, providing that there are the contact point will provide sufficient friction to hold the object, to balance the weight, etc. And with this concept in mind, we can formulate a robotic grasp as one optimization problem, which also often commonly used problem in model-based robot grasping synthesis. So this problem, the objective of this problem is to achieve a certain level of grasp quality, such subject to some constraints. For example, if you want to, there are multiple ways to grasp one single object. Even we want to grasp your mug, your coffee cup, you want to, for example, maybe you want to reduce the force so that you do not break the cup, or you want to save energy to increase the stability. So that said, we can use a variety of grasp quality metric in this problem. And with the concept of virtual finger, we can simplify the state space description, which is a dimensionality of X in this optimization problem. And also we need to consider multiple constraints, such as all the joints must lie within the joint limits, and the finger should not collide with each other, and we don't want the model penetration as well. So with this problem, after solving this problem, we are able to generate a variety of robotic grasps, where we see that robotic hand. So this is a 4-finger robotic hand. It's called an alligator hand. It has a 16-degree freedom with a 4-degree freedom for each finger. So we see that with after solving this problem, we're able to generate the grasp hand poses, which are not so often seen in the field. For example, you pinch one, you hold one object using the one finger and the palm, or you grasp the one finger, you wrap one object with one single finger, or you can also hold object using the side of the finger. Yeah. And so this is the first step to generate a robot grasp, and then come back to our original problem or original question, that how can we generate multi-object grasp? So the main challenge is, of course, we can, let's say we stick to the previous problem formulation. Let's do optimization again, but with more objects in the hand, we need to tackle multiple degree freedom at the same time. And also there are multiple objects. So consider each object should not collide with all the other fingers and should not collide with other objects. So this will largely increase the computational complexity and even makes this problem infeasible. So we reformulated the problem of grasping multiple objects to a multiple grasp of one single object. So what we have done is that we formulate an iterative process to exploit the kinematic redundancy, so which is refers to the degree of freedom in the robotic hand that you are able to control. So let me explain this process with this flowchart. We first start with a robotic hand with 0 degree freedom being used. Then we want to grasp the first object. Okay, so there are multiple ways to grasp it. They are all feasible. They are all potential candidates. They can be potentially used to grasp the object. Then we just synthesize a variety of grasps. Then we select the best one. So after grasping this object, there are still many joints in the hand can be used. So we may plan the grasp in the subspace of this hand pose. So actually, we see that in this, when we grasp the first object, it essentially consists of 2 steps. One is first is analysis. The second is grasp. Analysis means we analyze the hand structure to see what kind of which fingers we can use to grasp the object. Then the grasp is actually step is we actually generate a grasp and we select the best one. And so if then we just keep planning in the subspace of the kinematic structure. We just want to exploit the remaining degree of freedom. So we iterate this process again to grasp the second object and the third object until either all the objects have been grasped or there are no more degree of freedom available in the hand. Right? And since each grasp is actually it's generated in the subspace of the previous graph, so all the grasps they are independent of each other. So let's see. This is how we generate the sequence of multi-object grasp we generated. So it's a robot first grasp the first object, and then use an independent finger grasp the second one, and then the third one. But the question is, can we empower the robot to grasp even more objects? So we applied one strategy here, that is to prioritize the parsimonious grasp, meaning that since there are multiple ways to grasp one single object, we always prioritize the grasp hand pose that uses the least number of degrees of freedom, so that we can save more space or more degree of freedom in the hand to grasp subsequent objects. So after applying that strategy, our hand is actually to grasp 4 objects, which is quite challenging. You can try it at home to see if you're able to grasp how many objects you are able to grasp. So afterwards, we validated this on a real robotic hand. So we fixed the hand in the on this stand, and the hand was controlled on joint level, in that we control the joint configuration, joint positions of the finger, and the motion of the finger that was coupled with the motion of the object. So the hand of the finger, they only close when the object has reached to the desired grasp position. Then the finger will close and to secure grasp. Okay, so afterwards, let's move to another interesting problem is that once we grasp an object, how can we control the robot to manipulate the object, the so-called in-hand manipulation? In-hand manipulation is a very challenging problem because it contains dynamic interaction with the object, and we are dealing with a dynamic process. So here, for example, you want to move the finger below this bar and to grasp this object with 4 fingers, but it's quite challenging. This one failed because we see that the finger, so because we see that in the end of the video that the middle finger actually hit the object. Oh, sorry, yeah, the ring finger. And in this example, this is another typical failure, is that although the finger didn't hit the object directly, but the middle finger hit another finger and it causes this disturbance, so which led to the failure of this experiment. And in a successful trial, it will look like this, where the fingers should move carefully to avoid collision with other fingers and with other objects, and to secure the object in the end. Yeah. So it is a challenging problem because it requires motion that satisfy multiple constraints, multiple conditions. So first, the motion must be collision-free, as I said. So the finger motions, the finger should not collide with other finger, should not collide with the object, and also the finger should be able to adapt in real time, and also to afford interaction, meaning that the finger should be able to apply force on the object to change the state of the object. So our approach to address this challenge is using a sin neural distance function. So a neural distance function is actually a neural network. It is trained to approximate distance. So I will explain it in more details. So let's say the distance the f is a neural network, and the dx is a distance function with x being the state of the task, which contains the state of the robot and the state of the object. So we can consider it as a point in the configuration space. Yeah, and so ds it is distance function. Basically, it is the value, it is a scalar value that describes the distance from a point of interest to another point of interest. So if it is a positive value, means there is no collision. So if it is a 0, means the point is on the boundary. So if the ds is smaller than 0, then means these 2 points are in collision. Okay. So in this task, actually the sin neural distance function, it takes the input as I said. So the state in this task, it contains a robot joint configuration and also a spatial point of interest. If we want to grasp some object in space, we may consider that point as a point of interest, and output is a Cartesian space between that point to the surface of the robot. In our case, a robotic hand. Yeah. So to enable in-hand manipulation, we trained 2 models to neural distance functions. So one model is used to determine self-collision. Which means we have so the input is Q. Q is a vector of the robot joint configuration. It contains all the joint vectors. So think about moving your hands in different postures. Right, so each hand pose it corresponds to one joint configuration, can be described by a vector Q. And what this function does is that for each hand pose, for each Q, it calculates the distance between any 2 finger digits, anything 2 finger phalanges, which is described by D, this value. And then if all the D values are larger than 0, then means there's no self-collision of this hand pose. Okay, and a second model is a hand object collision model, is where we take another x additional input. X is a point in the space. Also as part of the input, then we calculate distance at d2. d2 is the distance from this point of interest, x, to any phalanges, any finger phalange of the robotic hand. Right, so let me explain this in this figure. For example, this is a robotic hand. There are 4, let's say there are 4 small obstacles denoted by the red dots in the space. Okay, so first the D1 is so one of the D1 between these 2 phalanges is actually the Cartesian space between these 2 links. Yeah. So if we have a point of interest in the space, so this point will be used as x coordinates in the second model. So and then we calculate this D is actually D2. It is a distance from this point of interest to the robot surface. So with this, and since we can infer the points in the space using parallel computation, which is quite fast in real time. So our trained neural network enables us to infer hundreds of thousands of points in a quite short time, which will afford us to adjust the robot motion in real time. And to use the model, we need hand configuration at every time step. And we also need objects. We need to know where the objects are. And since here in this example, the X is one single dot, one single point of interest in the space. And if we want to deal with a more complex object, we can describe the object using point cloud. So it basically is a set of points, and we can determine we can calculate the distance from each point in the point cloud to the robot surface and to see if the object is in collision with the robotic hand or not. So if there's no collision, so all the spatial points, all the configurations of the robotic hand that are collision-free, it consists of a collision-free joint C-space. C-space means a configuration space. Yeah. So within this collision-free configuration space, we're able to plan collision-free motions of the robotic finger. Right. So let me show this simple example, this visualization. Okay, so the robot wants to close its finger, and there's a moving obstacle in the space. And on the right side, it shows, okay, how this obstacle can be visualized in the joint space. Basically, we are projecting obstacle in a 3D Cartesian space to a joint space of the robotic hand. And the initial configuration of the robotic hand, which is corresponds to 1Q, is mapped on the right side as just one single point here. Right? So the target configuration is also mapped as one point on the right side. So then it's very clear from the right side which region. So basically the green region is collision-free, and the black contour means the boundary of this object, and the inside region, the red region means that it's inside object, so that the robot should definitely avoid. And with this collision-free joint space, we can integrate sampling-based planning method, planning algorithms to search for collision-free trajectory in space. So all these search algorithms enable us to search for collision-free paths in real time and adjust really quickly. And yeah, let's get back to the figure we saw before. So the robot in this example, in this scenario, the robotic robot want to close all its hands while avoiding collision with these 4 small dots in the space. So it is quite challenging because we need to control the 16-degree freedom at the same time, right, while avoiding collision with these, not only these dots, but also with other fingers. Yeah, and so this algorithm enables us to generate such a collision-free path. And also another very good feature of this, the collision-free joint space is that it affords contact aware force manipulation. So let's say if we want to maintain the contact force, so we can have the point moving on the contour, because all the contour lines represent the same contact force. We can just move along the contour line. And if you want to reduce the contact force, we just move away from the contour line. It's like you are moving your, thinking about you're pushing against the wall, then you move your hands further from the object. And if you want to increase the contact force, then yeah, you just move in the gradient descent direction. Yeah, so which is towards inside the object. Yeah. So with this, we're able to achieve a repositioning of one finger to avoid one object, to move it to the other side, while avoiding collision with object. And we can also control the robot to move the fingers, slide the fingers along the surface of the object. Just mention that the robot, we use cameras to capture the shape of the object, but the robot does not have knowledge of the shape of the object. So that means even for the very complex shaped objects, we don't need very specific, we don't need an explicit description of the object model and to plan the robot path on the object surface. We can do this very effortlessly. And in the last example, the robot is moving its fingers up and down, and the experimenter manipulates this wire, try to block the motion of the finger. And we see that even when the wire is being moved, the finger, they can still open and close freely without colliding the wire. So it also shows how efficient this algorithm is when being applied to this dynamic manipulation, especially to adjust the motion in real time. And finally, let's have a look at how can we connect all these one-shot actions, the simple manipulation task, to achieve more long horizon manipulation task. So there's all the large language models is very it's trending topic these days. It's having widely used in all the research fields and help us a lot. So what we want to do is we want to simplify robot programming. We want anyone, even without knowledge in robotics, can plan, can control the robots easily. Let's say, human workers, we want the robot to help us to grab something. So can we just turn the verbal description into some robot code that can enable the robot to accomplish the task? So a common path is to translate using large language models, translate human task description into robot command, then send to a robot to generate robot motion. Yeah. So the traditional way of planning a long horizon task relies on highly specific human knowledge. For example, you need to have a clear definition of the entire environment of the robotic system. You need to know the robot model. You need to know the environment. So what's inside the environment? So where is the object? And and when should you perform one robot action? And what is the consequence of this action? And what are the states that you can deter? You can say that, okay, the task is complicated. Basically requires an explicit description of the entire system. Yeah. So we want to simplify this entire process and using large language models to help us to achieve this goal. But of course, there are many challenges of applying LLM in the task motion planning. We may face in everyday life that when we talk to LLM, it may have some AI hallucination to give us some wrong answers, which seems plausible, but actually not true. And also, especially LLMs are very powerful, but also naive about the physics, especially of physical interaction in everyday life. So, and also it needs grounding and feedback to avoid or to correct these hallucinations to make sure that robot can perform the task safely and successfully. So in this work, we propose a framework to help improve the performance of integrating LLM into robot long horizon task motion planning. Let's say that we have the task, we want to clean the table in this in the kitchen. There are many different objects here, and there's a trash bin on the bottom right corner of the figure, and there's a sink on the top left corner of the figure. So we want the robot to be able to grasp different objects and put them in the correct place. So either throw them to the trash bin or put them in a sink for cleaning later. Yeah, so we want to tell the robot to clean the table, and Okay, so we give this the image and the task description to the large language model. So language model will extract the scene information, including objects and the locations. And we can also give some robot-specific information, such as what kind of actions can the robot perform, and what are the parameters of these actions. Of course, we can also provide optional information to the robot, which we consider as additional human instruction. For example, grasp that object carefully, do not break the glass, etc. And we consider this part as user input. Then from the large language model, it generates a plan for the robot to complete this long horizon sequential manipulation step by step. And then we evaluate this plan to simulation, and then we check how the robot model perform in the simulation. Then we record its performance, and we evaluate the performance. So, and if necessary, we can retune, we can feedback, give this information to the large language model as feedback to retune or to replan the originally generated task plan. And once this verification passed, we can send this task plan to the real robotic system to actually execute this task. And for the real robot system, very important part is that robot must have reliable controllers and also collision avoidance mechanism. Yeah, so this part we call the adaptation. So this two-level hybrid structure, it allows semantic reasoning and grounded execution for the robot to actually use LLM to tackle these challenging tasks in real life. There are several features of this framework. So first is context aware, because since it takes the image of this scene, this task as input, so we can explicitly request large language model to understand the underlying information of the task, which leverage the human prior knowledge. For example, if we want to grab a bottle, a glass of water, let's say, if you just plan the robot, you must explicitly control the robot to maintain the orientation of the hand so that you do not spill the water. And but this needs to be explicitly expressed to the robot by the programmer. But with a large language model, we can ask an LLM to take into consider these facts, this human prior knowledge, which is not explicitly contained in the program, to handle this task. So to decide what action to use and what are the constraints of this motion without explicit programming. And also, in order to guarantee that robot is able to perform what the language model is generated, we must provide a robot action set as well. Just in case the language model will generate some actions that beyond the capability of the robotic system. And with this feedback loop, we're able to validate the plan to make sure that the plan is optimized or is improved within the limited simulation trial. And this plan is 100% feasible for the robot to execute. And finally, we also must guarantee that all these, the robot controller must be reliable and adaptive in real world to handle any disturbance or perturbations, and also potential collision with other objects in the environment. So this is what it looks like in real robotics. They currently look like on real robotic system. So on the left side, it's a generated and tuned task plans. And so the robot just follows the plan, this sequential plan from top to bottom, and to execute the task and clean the objects one by one using the correct speed and grasp hand pose, and put object in the correct place. And also, as mentioned, it is very important to have reliable robot controllers to deal with real-world disturbances. We have our experimenter deliberately disturb the robot during task execution, and we see the robot, and thanks to the robustness of the dynamical system-based robot controller, so the robot is able to recover from the disturbance to its original path to continue completing the task. Okay, so finally, I want to summarize my talk today by discussing a bit about the path toward more dexterous robot or advanced dexterity. So the first work, I explained some generalization in robotic grasping, which is a fundamental skill of the robotic system to interact with the real world. It contains a high-dimensional contact choices, and also we need to handle multiple constraints. And from grasping, we discussed the robot manipulation. So how can we manipulate the object to interact with the object in a dynamic task to apply force and also to adjust the finger motion to interact in real time. And finally, we discussed how can we potentially to combine a sequence of manipulation motions to enable the robot to finish some long horizon sequential manipulation task. And the complexity actually keeps increasing from the bottom to the top, because grasping is it's more a static pose or configuration of the robotic system. But to manipulation, we need to consider how the robot handles the dynamics. And then to the long horizon, it's even more challenging because it relies on the causality of different steps of actions. And back to the question we discussed at the beginning of the talk. So what is the essential of human dexterity, and how can we enable robots to achieve high dexterity? Is that one very important feature of human dexterity is that it can be generalized across many dimensions. Let's say, still this example, when we grasp one object, we want to be able to build object. We want to grasp a different object, or we can want to extend this skill to our upper limbs, not only limit to our hands. So there are multiple dimensions that this skill can be generated. For example, to different tasks, environment, and embodiment. And the generalizable dexterity, it remains a holy grail in robotic dexterous manipulation these days. So basically, we want the robot skill to be able to generalized across these dimensions without retraining or reprogramming our robots. Yeah. Of course, there are multiple open challenges to truly generalizable dexterity. For example, is there a unified skill representation? So can we use a single foundation model maybe to handle the contact dynamics or deformation to apply to all the kind of objects, rigid objects and deformable objects, and also applicable to different robotic systems? Or if the skill acquisition can be scalable. So let's say we can consider a robot as a human baby is able to let the robot explore the world, interact with different objects in everyday life, and gain skills itself. And also, how can we actually transfer the skills to one task from one task to a different task, or to a different robotic system, or to a different environment? For example, some robots, they may work well on Earth, but how about we send robot to the moon, to the Mars, or underwater? The environment will also impose new challenges to the robotic system. So finally, I would like to say that advancing the robot dexterity is a very meaningful yet challenging research topic, because that will largely help us to improve the performance of robotic system in multiple disciplines, not only industrial manufacturing lines, but also for the surgical robots, agricultural robots, or prosthetic arms. Yeah, so the improving robotic dexterity will certainly help us to shape the future of the robot manipulation and the future of our world. Thank you.
Thank you very much.
Yes, please.
When you had the optimization of drafting motions,
Yeah.
so I think it's a step 2 in your pyramid of the example you gave, you had 16 degrees of freedom for the hand.
Mhm.
I imagine the topology of that space is going to be very unpleasant,
Mhm.
the optimization space. And then you add in the collision constraints as well.
Mhm.
What kind of algorithm were you using to optimize over trajectories in that space?
Are you referring to the first work of robot grasp synthesis, how we generated the grasp of one particular object?
So you had an animation with the streamlines showing the space.
Oh, okay, the in-hand manipulation one.
Yes.
Okay, yeah. Yeah, and so sorry, your question is
My question is, what algorithm were you using to find the good trajectories in that space?
Actually it's so this approach, the neural disk function, it creates a free collision-free joint space. So basically you can consider it as a 16-dimensional space, but with all the regions that they are collision-free. So actually any search algorithms can be applied to find a path in this high-dimensional space. And in this work, we're using RT and PRM. So it's just a traditional search algorithms that you start from the initial configuration, then you sample batch of points, you find which point there is collision free, then you attach to your search tree, then you can finally until until you reach to the target configuration. It's not limited to, it does not impose any specific requirements for the search algorithm. Yeah, it's more the concept of constructing a collision-free space where basically any path in this collision-free space from the starting configuration to the target configuration is a possible solution. It's just a matter of complexity of real robot. Yeah.
So basically the neural network has done the hard bit. That's already
Right.
transformed your space to be nice.
Yeah.
And you can use the
so right. One advantage of using neural network in this example is that it's really fast. So it enables us to infer thousands of points within milliseconds, and so that we can almost have one to capture the entire collision-free space in real time, so we can update the robotic system really quickly. Okay.
In the tidying task, before you'd used point clouds to embed those objects. Did you also use a point cloud when you're doing the tidying task? The multiple items on the table, is that just another?
Oh no, that one in that task we didn't use point cloud. We used a motion capture system. So motion capture system, the system is used to track objects within the scene. So we put some markers on the object. So we need at least 3 markers to define a rigid body in the motion capture system. So actually in the video, you could see that there are multiple markers attached to each object, and there is a camera array mounted on the ceiling, so which is used to capture everything from the, So with the motion capture system, we're able to to obtain the real-time position and orientation of each object, so that the robot knows where the object is. and yeah, the robot can go there.
So the camera's just feeding back like raw footage.
Yeah.
Do we think embedding like a semantic segmentation process might make it more generalizable?
Oh, that's a very good idea. Yeah, definitely. So I think, well, that could be a very good extent of the work that we, without relying on the motion capture system, we can even, so with that implemented, the robot may even perform variety of tasks based on a single camera. Yeah, I think that's a very good idea. Yeah.
Yeah, I got two questions. One is sort of about the way you use the neural network to reduce the space for the manipulation task. I was just wondering, what is like the sort of traditional method of doing that? Is it just a kind of brute force search for which routes are possible, or what was the previous method before you developed the neural network approach?
The traditional method of tackling this problem are mainly two aspects. So first is learning-based methods. For example, reinforcement learning, where you can actually what you train is you let the robot learn from trial and error. You sort of, so in each rollout, you just let the robot, the control robot, to move to a target. And once the robot hits a obstacle and fails, and you keep it this iteration to learn a feasible policy to drive the robot from the target to from the initial point to the target. Or there's another way it is purely model-based planning of where you have information of the obstacles in the space. You have your robot hand model. So what you want to do is you control each of the finger to move to the target without colliding the obstacle. So that involves path planning. So you basically control one point from which is your initial it's the initial configuration to its initial target configuration. Then you want to generate a path. Right? So from this point to that point in the Cartesian space, you can even use inverse kinematics to solve for a possible joint trajectory. And but it's very complex because you need to explicitly design the sequence of finger motions. Maybe, yeah, I'm just thinking, if I were to program such a task, I probably need to define the sequence of motion for the fingers. Right, move one finger first, then followed by another finger. But yeah, don't move all fingers at once so that you can simplify the problem a little bit.
I guess for these older methods, it would be difficult to generalize between different objects. Right, if you're using a different object, you would need to almost do the same thing again, quite possibly.
Yeah, exactly.
With the newer method, you can just run it, I guess.
Yeah, that can be easily generalized to different objects, because all you need is actually a point cloud of the object. Yeah.
My other question was on the long-term task planning, the final bit. I was just wondering, when you said that you were retuning, you run a simulation and you retune your LLM output.
Yeah.
How exactly? I'm just wondering, how exactly are you doing the retuning? Yeah.
Oh, okay. So the idea is we first give the LM generates a plan. We give this plan to simulation. We simulate a robot in a simulation environment where we were using Mojuko, and to observe the output. For example, if we observe anything, for example, when the robot collided object or robot moves too fast and so the water spilled. In such cases, we just so we log all the output of the task and use that as feedback to the large language model. And so yeah,
So you literally just like kind of put those outputs into the large language model, as in like just saying this was in just like word format. This is wrong. Please do this. Is that? And then or
No, so we give the output. So it's so in numbers. So yeah, it's a more like a quantitative output. We design multiple metrics to evaluate the performance of the task. Also the any information during the simulation is also available to LLM, such as the speed of the robotic arm and the position of the object, and whether there are instances of failures observed or occurred during the simulation. So this information were all used to as an experimental log to fed back to LLM so that the large model is able to identify where the failure happens and what could be the factor that led to these failures, so they can tune the robot motion. For example, if the robot moves too fast and the object I'll take one example of the grasping. Okay, so if the robot grasps the object and moved to the thing, but the object dropped, so that implies the grasping force is not enough. So with this feedback, the language model will retune this action to increase the grasping force in the next trial. Yeah, or if there is a error in the logical sequence where the task 1 need to be performed before task 2, but M swapped these orders, then this will be identified as a logical error, and it will trigger reply instead of retune.